Effective preparation is key to success. Firstly, review all material thoroughly. Go over everything covered, including notes, textbooks, and practice exams. Focus on understanding the concepts rather than just memorizing facts. Secondly, identify weak areas by taking practice exams or reviewing past questions to determine which topics require extra focus. Dedicate more time to studying those specific areas. Thirdly, practice with sample questions. Solve as many practice questions as possible to familiarize yourself with the format and types of questions that might be asked. On exam day, it is important to arrive early, allowing ample time to get to the testing center and settle in. Carefully read all instructions on the exam to ensure a full understanding of what is expected. Manage your time wisely, allocating time for each section based on its difficulty and importance, avoiding spending too much time on any single question. If unsure about an answer, make an educated guess, and if you can eliminate some options, your chances of guessing correctly increase. Utilize any scratch paper provided to note down important information or calculations, which will help stay organized and avoid mistakes. If time permits, check your answers to ensure they make sense and are complete. For exams with specific emphasis, understand relevant laws and regulations. Make sure to have a strong understanding of these laws. Be familiar with relevant case law. Exams may include questions based on case law. Familiarize yourself with important cases and their holdings. Practice multiple choice questions extensively to improve your chances of selecting the correct answer, especially for exams that primarily use this format. Use available tools like highlighters and annotation features during the exam to mark important information and make notes to help you remember key points. Manage time effectively during longer exams to avoid running out of time and missing questions. Consider this example of calculating voltage drop. The formula for voltage drop in a direct current circuit is voltage drop equals current times resistance. Let's say you have a direct current circuit with a current of 20 amps and a resistance of 2 ohms. The voltage drop would be 20 amps times 2 ohms, which equals 40 volts. In alternating current circuits, the formula is a bit more complex due to the presence of reactance. The voltage drop formula for an alternating current circuit is voltage drop equals current times impedance, where impedance is the total opposition to current flow, including both resistance and reactance. To calculate impedance, you need to know the resistance and reactance of the circuit. Impedance, Z, is calculated as the square root of resistance squared plus reactance squared. For example, if you have an alternating current circuit with a resistance of 3 ohms and a reactance of 4 ohms, the impedance would be the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which equals the square root of 25, which equals 5 ohms. If the current in this circuit is 10 amps, the voltage drop would be 10 amps times 5 ohms, which equals 50 volts. When working with three-phase systems, the voltage drop calculation depends on whether the system is balanced or unbalanced. In a balanced three-phase system, where the loads are evenly distributed across all three phases, the voltage drop is the same in each phase. The voltage drop can be calculated using the line to neutral voltage and the impedance of the phase conductor. The formula for voltage drop in a balanced three-phase system is voltage drop equals square root of 3 times current times impedance. For example, if you have a balanced three-phase system with a line to neutral voltage of 120 volts, a current of 15 amps, and an impedance of 2 ohms, the voltage drop would be approximately 1.732 times 15 amps times 2 ohms, which equals approximately 51.96 volts. In an unbalanced three-phase system, where the loads are not evenly distributed across all three phases, the voltage drop will be different in each phase. To calculate the voltage drop in an unbalanced system, you need to analyze each phase separately. You can use symmetrical components to simplify the analysis. Symmetrical components break down the unbalanced system into 3 balanced systems: positive, negative, and zero sequence. The voltage drop in each sequence can be calculated separately, and then the results can be combined to find the voltage drop in each phase. Accurate calculation of voltage drop is crucial for ensuring the proper operation of electrical equipment and maintaining system efficiency. Insufficient voltage can cause equipment to malfunction or fail, while excessive voltage drop can lead to energy waste and increased operating costs. The electrical codes, such as the National Electrical Code, provide guidelines and requirements for voltage drop calculations to ensure electrical systems are designed and installed safely and efficiently. The National Electrical Code Section 210.19 A1 Informational Note Number 4 recommends that the voltage drop on a branch circuit should not exceed 3% at the furthest outlet of power, heating, and lighting loads, or combinations of these. Furthermore, the maximum voltage drop on both branch circuit and feeder should not exceed 5% overall. The National Electrical Code Section 215.2 A3 Informational Note Number 2 recommends that the voltage drop on a feeder should not exceed 3% for power, heating, and lighting loads, or combinations of these. Furthermore, the maximum voltage drop on both branch circuit and feeder should not exceed 5% overall. Factors that affect voltage drop include conductor size, conductor material, circuit length, current, power factor, and temperature. Larger conductors have lower resistance, which reduces voltage drop. Copper conductors have lower resistance than aluminum conductors, resulting in lower voltage drop. Longer circuits have higher resistance, which increases voltage drop. High current results in greater voltage drop. Lower power factor increases voltage drop. Higher temperature increases conductor resistance, which increases voltage drop. To minimize voltage drop, you can use larger conductors, reduce circuit length, use copper conductors, reduce current, improve power factor, and lower operating temperature. Conductor sizing is an important consideration in electrical design to ensure that conductors can safely carry the intended load current without overheating. The National Electrical Code provides tables and guidelines for determining the appropriate conductor size based on the ampacity of the conductor. Ampacity is the maximum current carrying capacity of a conductor under specified conditions. The National Electrical Code Table 310.16 provides ampacity ratings for various conductor types and sizes based on temperature rating and installation conditions. When determining conductor size, you must consider the ampacity of the conductor, the ambient temperature, the number of conductors in a raceway or cable, and any other applicable derating factors. Derating factors are used to reduce the ampacity of a conductor when it is installed in conditions that reduce its ability to dissipate heat. For example, if conductors are installed in a hot environment or bundled together in a raceway, their ampacity must be derated to prevent overheating. The National Electrical Code provides derating factors for various conditions, such as ambient temperature correction factors and adjustment factors for the number of conductors in a raceway or cable. It's important to select conductors with sufficient ampacity to handle the expected load current while accounting for any derating factors to ensure safe and reliable operation of the electrical system. Overcurrent protection is a critical safety feature in electrical systems designed to protect conductors and equipment from damage caused by excessive current flow. Overcurrent protective devices, such as circuit breakers and fuses, are used to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are electromechanical devices that automatically trip and open a circuit when an overcurrent condition is detected. Fuses are overcurrent protective devices that contain a fusible link that melts and opens the circuit when an overcurrent condition occurs. The National Electrical Code requires that overcurrent protective devices be selected and installed to protect conductors and equipment from overcurrent conditions. The overcurrent protection device must have an ampacity rating that is equal to or less than the ampacity of the conductor it is protecting. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protection device based on the type of load, the conductor size, and the insulation conditions. When selecting overcurrent protection, it's important to consider the interrupting rating of the device. The interrupting rating is the maximum fault current that the device can safely interrupt without being damaged. The interrupting rating of the overcurrent protection device must be equal to or greater than the available fault current at the point of installation. Grounding and bonding are essential for electrical safety and are designed to provide a low impedance path for fault current to return to the source, minimizing the risk of electric shock and fire. Grounding is the process of connecting the electrical system to the earth, providing a reference point for voltage and helping to stabilize voltage levels. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together, creating an electrically conductive path that allows fault current to flow back to the source. The National Electrical Code requires that all electrical systems be properly grounded and bonded to ensure electrical safety. Grounding electrodes, such as ground rods and grounding plates, are used to connect the electrical system to the earth. Bonding jumpers are used to connect metal parts of the electrical system together, such as metal conduits, metal enclosures, and metal equipment frames. Ground fault circuit interrupters are devices that are designed to detect ground faults and quickly interrupt the flow of current to prevent electric shock. Ground fault circuit interrupters are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Electrical plans are essential for the design and installation of electrical systems. Electrical plans provide a detailed representation of the electrical system, including the location of electrical equipment, wiring diagrams, and circuit schedules. Electrical plans are typically prepared by qualified electrical engineers or designers and are used by electricians to install the electrical system according to the design specifications. Electrical plans should include information such as the location of electrical outlets, switches, lighting fixtures, and electrical panels. Wiring diagrams show the connections between electrical components, including the size and type of conductors. Circuit schedules provide information about the loads served by each circuit, including the ampacity of the circuit and the overcurrent protection device. Electrical inspections are conducted to ensure that electrical installations comply with applicable codes and standards. Electrical inspections are typically performed by qualified electrical inspectors who are employed by local government agencies or third-party inspection agencies. Electrical inspections are conducted at various stages of the electrical installation process, including the rough-in inspection, the final inspection, and the periodic inspection. During the rough-in inspection, the electrical inspector verifies that the wiring and grounding system are installed correctly before the walls are closed up. During the final inspection, the electrical inspector verifies that all electrical equipment is installed properly and that the system is safe to energize. Periodic inspections are conducted on existing electrical systems to identify any potential safety hazards or code violations. Electrical safety is of paramount importance, and it is essential to follow safe work practices when working with electricity. Always energize circuits before working on them, and use appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work on electrical equipment when you are wet or standing in water. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Always follow the National Electrical Code and other applicable codes and standards when installing and maintaining electrical systems. Regular maintenance of electrical systems is essential to ensure their safe and reliable operation. Inspect electrical equipment regularly for signs of wear and tear, and replace any damaged or worn components. Test ground fault circuit interrupters periodically to ensure that they are functioning properly. Keep electrical panels and equipment clean and free of obstructions. Follow the manufacturer's recommendations for maintenance and service of electrical equipment. The NEC is updated every 3 years, so it's important to stay current with the latest requirements. Changes can include new articles, revised tables, and modified definitions. Participating in continuing education courses, reading industry publications, and attending seminars can help you stay informed. It's important to understand the proper use of electrical testing equipment, such as multimeters, clamp-on ammeters, and insulation testers. Incorrect use can lead to inaccurate readings or even damage to the equipment. Before using any testing equipment, read the manufacturer's instructions and familiarize yourself with its features and limitations. Multimeters are versatile tools that can measure voltage, current, and resistance. Clamp-on ammeters are used to measure current without interrupting the circuit. Insulation testers, also known as megometers, are used to measure the insulation resistance of conductors and equipment. Understanding electrical drawings and diagrams is crucial for electricians and electrical engineers. Electrical drawings provide a visual representation of the electrical system, including the location of equipment, wiring, and control circuits. Common types of electrical drawings include single-line diagrams, which show the main components of the electrical system and their interconnections, and wiring diagrams, which show the detailed wiring connections between components. Symbols are used on electrical drawings to represent different types of electrical equipment and components. It's important to be familiar with these symbols to accurately interpret the drawings. NEC Article 100 provides definitions for many common electrical terms. Understanding these definitions is essential for applying the code correctly. Some key definitions include ampacity, which is the current carrying capacity of a conductor, and voltage drop, which is the decrease in voltage along a conductor due to resistance. The NEC covers a wide range of topics related to electrical safety. Some important areas to focus on include grounding and bonding requirements, overcurrent protection, wiring methods, and equipment installation. Grounding and bonding are essential for protecting people and equipment from electrical shock. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors and equipment from overloads and short circuits. Wiring methods specify the types of wiring allowed in different locations and applications. Equipment installation requirements ensure that electrical equipment is installed safely and correctly.